Okay.
Hi, everyone. Good afternoon. It's a pleasure to welcome Professor Lorena Bociu from the Department of Mathematics at North Carolina State University in our event. I will just give some words about the Professor Lorena. She earned her PhD in 2008 from the University of Virginia under supervision of Professor Irena Lazieska. Uh, Her area of research is in analysis and control of PDEs, okay, with application in nonlinear waves, equation, fluid and structure, and among others situations. And today we have a very good opportunity to see the lecture of her. We'll try it about multiscale interface coupling of PDEs and ODEs for tissue perfusion. Thank you, Professor Lorena, and you can start.
Thank you so much. Thank you all for being here. First, I would like to thank Professor Juan Limaco for the invitation and Roberto for the nice introduction. The Seminario De Edp Matematica Aplicada is a great initiative, and I'm very happy to be part of it. So thank you. So let me start with the motivation for our work, why we care about this multi-scale interface couplings between partial and differential equations, ordinary differential equations. So here's the main idea. We have a local region of interest for which we provide an accurate three-dimensional description, but at the same time, we want to account for the global features of the problem, and we do that by introducing a so-called reduced 0D model. So 0D meaning that there is no space dependence, just time dependence. So we're talking about systems of ODEs. This multi-scale strategy has been very successful in physiological flows. For example, when we have blood flow in arteries or airflow in the bronchial tree. This is the case where Stokes or Navier-Stokes equations for a specific part of an artery are coupled with this systemic zero-dimensional lumped circuit models, which approximate the remainder of the circulation. And there's lots of papers in this field. Here I'm mentioning just a few of them by Quereroni, Gramont, Bafico, Caricino, and their collaborators. In comparison, our focus is on biological models where the perfusion of a specific tissue or organ, which is our local phenomenon, is studied in correlation to the global features of the surrounding blood circulation. Why? Because we know that there are many pathologies that are related to the hemodynamic changes that occur at the microvascular level, where we have small vessels that pier the tissue and perfuse it with blood. So because we work with a large number of these very small vessels, it is impractical to model each one of them separately using either Stokes or Navier-Stokes equations, as it is done for the large arteries. So what we do to address this issue, we use fluid flow through deformable porous media, which are models that were proposed for tissue perfusion, where the blood vessels are modeled as pores within a deformable solid that represents the tissue. So for the local problem, as I said, we're using fluid flow in deformable porous media, basically poroelastic systems, right? So these are systems of PDEs that describe this fluid-solid mixture as a continuum body, where we account for the complexity of the microstructure via effective parameters. So for the mathematical setting, we have our domain omega in R3. For each position vector x, at each position, we have the representative volume, V of x, which of course is made up of the fluid volume and the solid volume. And as usual, we introduce the volumetric fraction, the quotient between the volume of the solid and the total volume, and this is known as porosity. And we also have the counterpart for the solid, right? Phi sub s, which is the quotient between the volume of the solid over the total volume. And we work under the assumption of fully saturated mixture, so the sum of the two phis add up to 1. So in general, this is how a fully dynamical poroelasticity system looks like, right? We have two balance laws. I wrote it here in terms just of the two main variables, the solid displacement or elastic displacement U and the fluid pressure P. So the first equation is the momentum balance equation for U. The second equation is the mass balance equation for the fluid pressure P. As I said before, we are assuming full saturation, but also small deformations for the homogeneous porous medium. And what really mathematically that translates into is if you look at the second and third term in the first equation, you recognize that if I can combine those into minus divergence of a elastic stress tensor, linear elastic stress tensor, okay? Now, let me introduce everything that appears in this model. So in order, what are the key parameters? Of course, rho, as usual, is the density of the porous permeable medium. Lambda E and mu E are the Lamé parameters of elasticity. Here, alpha is called the Biot-Willis constant. This is strictly positive, and it accounts for the pressure to deformation coupling, because as you can see, it shows up in the first equation in front of the gradient of the pressure, and in the second equation in front of the divergence of U, which is the solid dilation. And C naught is the constraint storage coefficient, which combines the porosity of the medium and the compressibility of the fluid. Of course, we have sources. So on the right-hand side, F in the first equation is the elastic body source. S in the second one is the fluid source. The other things to note here is the only term that's time differentiated in the second equation, right? This first term together is known as the fluid content zeta. So zeta equals C0P plus alpha solid dilation. And the second term K shows up. This is the permeability, and I will talk more about this on the next slide. These models have lots of applications, from settlements of soils under load to wave propagation in fluid saturated porous media to tissues and organ perfusion. In fact, these models were inspired by geophysics and petroleum engineering problems, where you have fluid that flows through sand and rocks. From the mathematical point of view, the first paper that dealt with this was a paper by Terzaghi in 1925, where he focused on a one-dimensional model for these problems. And it was around 1940s that Maurice Biot started working on this and truly developed the field of poroelasticity, working on the three-dimensional scenario and started the whole well-posedness theory. And after that, there's a lot of work in the literature related to this. Here I'm just mentioning a few of them. Of course, the list is non-exhaustive. But again, the focus in most of them is on geophysical applications. So the poroelastic structures are really soil and rocks. But more recently, there are many applications coming from biology, medicine, and bioengineering that require the use of these systems, because we have fluid flows inside cartilages, bones, and engineered tissue scaffolds, as well as blood flow through tissues in our human body, like the brain, the liver, and the eye, which is I included a picture of here on the right, because this is what motivated our work, and I will tell you more about it in a couple of slides. So because we are focusing on these biomedical applications, there are a few things that we need to take into account in the model, right? So number one, inertial effects are negligible. So that means that the first term in the first equation disappears. There's no UTT there, right? So mathematically, that means that if before this was a hyperbolic parabolic coupling, now we have an elliptic parabolic coupling. And this is what's known as a quasi-static deformation. Now, if you want to think of this in a very formal operator, theoretical operator form, what I can do here is combine these two terms, which I already told you, you can write it as minus divergence of an elastic stress tensor. So think of that as formally, this is my elasticity operator E applied to the solid displacement U. Move the fluid, the gradient of the fluid pressure on the right-hand side. And then in the second equation, you can recognize that the second term is kind of like a diffusion operator. Imagine that K is just a constant, of course, that just becomes, Laplace of P. So let's call that A of P, right? Diffusion type of operator. Now, the next thing to consider is the fact that biological tissues have a mass density close to that of water. So that means that we are working in the scenario of incompressible fluid and solid constituents. Now, if you're a fluids person, you're immediately going to say, oh, so divergence equals 0. No, this is not what is meant in this case. So when we say incompressible fluid and solid constituents, what is meant is that the solid and fluid phases cannot undergo volume changes at the microscale. And mathematically, that translates into the following things. So this constraint storage coefficient C naught disappears, it's 0, right? And alpha, the Biot-Willis constant, the coupling constant, equals 1. The details can be found in the paper by Detourné and Cheng. So that means that the fluid content simplifies to just being the solid dilation, so the divergence of U, which I then replaced here in the last equation. So that means that the whole system can be written as one implicit degenerate evolution equation if I use this pressure to dilation operator B. So really what happens, ignore the source F on the right here. You can easily translate it, right? So what I can do is I can solve for U in terms of the fluid pressure P by applying the inverse operator of E, right? Then I apply divergence and then I plug it in into second equation. So it becomes the time derivative of B applied to P plus diffusion operator A applied to B equals some source on the right-hand side. Why is it called implicit? Because in the equation, we have the time derivative, not of the variable P, but of the operator B applied to P. And then it degenerates because in some cases, the kernel of B can be non-trivial, okay? I mentioned this because later on when I give a brief summary of the well-posedness results related to the system, this will come back. Now, another challenge motivated by biological structure is that the permeability that shows up in the system is in general not a constant. So the scenarios, either you take it a function of space and time, or the most general one is to have a nonlinear function of the solid dilation, so divergence of U. What kind of nonlinear function? Well, that depends on the pore architecture inside the body and also properties of the fluid. There are two main scenarios. So if you have Newtonian fluid that flows between spherical particles, then the formula is the so-called Kármán-Kozeny formula, where K is given as this quotient between a cubic and 1 minus x squared. The other scenario is where Newtonian fluid flows inside cylindrical pores, and this is when the permeability is taken as a quadratic function. Okay, but either way, it's a nonlinear function, and it's a quasi-linearity that is not monotone in the system. Okay, now if you're familiar with this equation, you also know that this whole term that shows up under the divergence operator in the second equation is known as discharge velocity. So V equals minus permeability, which is nonlinear in general, a nonlinear function of the divergence of U, and then gradient of P, and this is the discharge velocity. So now that I described the local problem, so we introduced the system of poroelasticity, how do we account for the global features, right? So this is kind of a schematics for the physics of the coupling, right? So we introduced the poroelastic, also known as Biot model, because as I told you, Biot started this whole theory in the 1940s. And what do we do now? So now, this is the lumped circuit that we use to model the global features. So here, the fluid flow through a hydraulic network is described via its analogy with current flowing through an electric circuit, okay? Where we have active sources of voltage and current. They correspond to pressure and flow rate sources, resistances to viscous effects, inductances to inertial effects, and capacitances to vessel compliance. So these are known as RCL circuits, okay? Resistors, inductances, capacitances, and they can be nonlinear time invariant. This would correspond to vessel deformability and remodeling, or you can assume that they're linear time invariant elements if the vasculature is compliant but with small deformations and passive. So following the book by Desur and Ku in 1969, when all this was introduced, we have the state variables for each inductor and capacitor in the circuit. I should have mentioned that for what we did here, we basically split this lump hydraulic circuit into the connection, which we call lambda. This is what connects the circuit to the poroelastic model, and then the internal circuit, upsilon tilde, which we assume it has N sub R resistors, N sub C capacitors, and N sub L inductors. For each inductor, we have the volumetric flow rate across the inductor, which we call Q. For each capacitor, we have the pressure difference across the capacitor, for which we use the capital letter pi. Now, inside the connection, we assume that the capacitor here is set to ground, where we assume zero pressure. So the difference between across this capacitor becomes just little pi, and we call this little pi instead of capital Pi to separate it from all the other ones, because this is the one where you truly see the connection with the PDE model. So it will show up in the equation of the PDE, so to kind of set it apart from the other variables. Okay, so then we have the vector of state variables, which we called Y for the lump hydraulic circuit, which has 1 plus n sub c plus n sub l variables. And then, as I told you, the little pi is the first one, and that's the most important one, as you will see. And here's how the ODE for the lump circuit looks like. So it's a nonlinear ODE. Let me describe everything that shows up in here. So A is a d by d tensor that may depend nonlinearly on time and also on the state variable Y. S is basically a source. It's a d by 1 vector representing the sources of pressure and flow rate that may be present inside this internal circuit. And the last term is really where you see the contribution from the connection between the circuit and the BO model. So this is a function of Q. Who is Q? If you look in the picture right here, this is the flow rate across this resistor here, Q, right? So this last term is really just only the first component is non-zero, and it's proportional to Q, right, which is the volumetric flow rate through the connecting resistor. So this is where you see the connection between the PDE and the ODE. Of course, we now have to also introduce boundary conditions and interface conditions. So for boundary conditions, let me focus on the PDE model first. And here, we split the boundary. Think of it as the boundary that has nothing to do with the ODE, and then the interface, which is called sigma. So let me start with gamma, the other part of the boundary, right? So of course here we introduce boundary conditions. What kind? So first we split the boundary between gamma D and gamma N, exactly what you would think, D standing for Dirichlet, N standing for Neumann. So Dirichlet boundary condition with respect to solid displacement, Neumann boundary condition. So as you can see on gamma D, U equals 0. On gamma N, we have this Neumann type boundary condition, right? So total stress dot N equals some given source G. But of course, we also have to give boundary conditions for the fluid, right? For the pressure and discharge velocity. So what we do, we split the gamma D part into two parts, gamma dP, which on this part pressure equals 0, and gamma dV, where we have a Neumann type boundary condition for the pressure, because remember, discharge velocity is kind of like gradient of pressure. So this is gradient pressure dot N equal given source psi. The last two you don't need to focus much on. These were included here just because they're instrumental for the derivation of the associated one-dimensional model. So I will skip those. The most important thing here is how are the PDE and ODE coupled, right? So what is happening on sigma? How are we coupling these two? Because this is the subtle issue, right? You have on one side PDE, which requires pointwise conditions. On the other side, you have the ODE, which works with mean data, right? So how do we couple the two? So let me start with the simplest one, where what assumptions are we making for the solid displacement? So we assumed here that U equals 0 on sigma. Of course, we can make we can include other options here depending on what you're modeling. Now, what we know is that Poiseuille's law, which is the analog of Ohm's law, has to hold for the resistor that connects the circuit to the BO model. So what that means is this flow rate Q has to be proportional to the difference between these pressures, right? The pressure on this side of the circuit, which is little pi, and the pressure that comes from BO, which we called capital P, right? So we know that this has to hold. Now, we also have to make sure continuity of pressure is maintained, right? Between the capital P here and also the BO pressure. So how do we do this and at the same time maintain Poiseuille's law? So here we consider two cases, and we call them either pointwise pressure condition or integral pressure condition. So the first one is to assume that the two pressures are equal. And if we assume that, in order for Poiseuille's law to hold, we have to add another condition. So this becomes a non-local type of condition. So the flow rate Q has to equal this integral over sigma of discharge velocity dot N. Okay, so this is one way. The other way is to assume that the pressure here at this node that connects to the circuit is the average of the BO pressure on the interface sigma. Okay, and then accordingly, to make sure this Poisson law holds, we have now this condition, which looks more like a normal Robin type boundary condition for BO. Okay, because this again, there would be like grad P dot n, so Neumann, but you also have P, so Robin boundary condition, and you have this pressure pi that comes from the circuit inside here. Okay, so these are the two conditions that we investigated. How this is not they came from the physics of the problem, but at the same time, looking in the literature, we found out that these were similar to what was used before in the multiscale strategy for when they couple the Stokes or Navier-Stokes with ODE systems, okay? And you can find that in the paper by Quarteroni and Veneziani, where they describe these so-called natural interface conditions, which were inspired by a paper by Haywood, Ranecker, and Turek, artificial boundaries and flux and pressure conditions for incompressible Navier-Stokes equations. Now, the choice of which interface conditions to adopt, it should be part of the modeling process, right? And driven by the problem you're modeling, okay? We investigated both of them, and we have a recent paper where we did that, so I listed that there. Numerically, we look at them and how the solution is different between the two scenarios. To the motivation, and really this is how everything started long time ago. And what motivated the work is we were interested in perfusion in the optic nerve head inside the eye and its relation to the development of neurodegenerative diseases, one of which is glaucoma, also known as the silent thief of vision, because what happens is it leads to irreversible loss of vision. Okay, and up to now, intraocular pressure, elevated intraocular pressure, which is the pressure inside the eye globe, is the only treatable risk factor for glaucoma. So this is if you do your eye annual checkup, or if you have glasses, you know they always do that puff inside your eye. That's how they measure your IOP, and they do that for anytime you go to your eye doctor. On the right, you can see how this disease affects vision. So normal vision, and as the disease progresses, basically you lose vision from the periphery to the middle of the eye. So in extreme glaucoma, the person only sees through a very small tube in the middle of their eye. Now, I included here a detailed picture of the optic nerve head to explain a little bit what part we were focusing on. So the vision, for those of you who like biology, right? So it's the retinal ganglion cells that relay the information from the eye to the brain. The retinal ganglion cells go through layers here in the optic nerve head, one of which is this porous deformable tissue at the base of the optic nerve head called the lamina cribrosa, okay? So the axons, the retinal ganglion cells axons, bundle up and they go through this tissue on their way to the brain. So now it is believed through clinical research that it's the biomechanics of this tissue that plays an important role in glaucoma. So whatever happens here, it could be that they're pinching the axons, it could be that, the capillaries inside this tissue break. Somehow this is connected to the development of the disease, okay? But as I said before, the only thing that currently they can treat is elevated intraocular pressure, because it's believed that that somehow messes up the biomechanics of this tissue, right? And they do that either by using eye drops in the eye, or if those don't work, then you can do some type of laser surgery where they drill some holes to release some of this pressure, okay? However, there are many individuals with elevated IOP that never develop glaucoma, while at the same time, about a quarter of IOP-treated patients continue to progress to blindness. So clearly there is a significant evidence that there are other vectors involved in the disease. The intraocular pressure is not the only risk factor. So when we started looking at this, we said, okay, just focusing on the local problem, if we just focus on the lamina cribrosa, this tissue, right, which we can model using poroelasticity, we should also think about viscoelasticity, because mechanical tissues are both elastic and viscoelastic, right? Why? Because they contain elastin, but also collagen, right? Collagen stands for viscoelasticity. And it is known that structural viscoelasticity decreases with age and disease, right? At a certain age, our body's production of collagen dramatically decreases, okay? Hence wrinkles. And this not just happens to our face, it happens actually in our entire body, okay? And collagen structural changes have been found in patients with glaucoma. So from the mathematics point of view, okay, we have poroelastic system, but let's account for structural viscoelasticity in the system. So let's look also at poroviscoelastic models. So what we did is, remember, this is how the system that I introduced, the PD system that I introduced earlier, looks like. And what we did was we said, okay, instead of just having elastic stress tensor, let's introduce a viscoelastic stress tensor. Basically using the same formula as before, but now everything depends on U sub T. This is a Kelvin-Voigt type of damp. It's like a damping, right? You introduce viscoelasticity of Kelvin-Voigt type. And now the total stress is not just elastic, but also viscoelastic. So it has the elastic component, but also T sub V. And we included this parameter delta in front of it to basically indicate the extent to which our model has viscoelastic effects, right? So if I tell delta to be 0, I'm back in the poroelastic scenario, okay? And this is the total stress. As before, of course, you also have to include the pressure, the fluid pressure inside the stress. That was there also before. So the only novelty now is that we have the extra term. And this is, as you can see, almost 10 years ago when we started looking at this problem, where we wanted to have a comparison between two models, poroelasticity and poroviscoelasticity, and see what happens. Now, as I promised, here's the quick summary of what Posner's literature for poroelasticity. So, of course, there are different stage. Which system are you looking at? And the easiest ones are the linear poroelasticity, right? When you assume that the permeability K is just a constant, right? So now you have a linear coupling. Of course, delta is 0 because everyone was just looking at poroelasticity alone with no viscoelasticity. The first paper in our knowledge that dealt with this system was a paper by Oriol and Sanchez Palencia in 77, but they looked at the case of compressible constituents. So C naught is strictly positive. There were no sources, and they had the most simplified boundary conditions for both U and P, so homogeneous Dirichlet boundary conditions. Now, I should point out that if we're in the case of compressible constituents, the problem becomes much easier. Why? Remember, I mentioned that the whole system can be formally thought of as this one implicit evolution equation after you introduce the pressure to dilation operator. This pressure to dilation operator, it's not a nice operator. It is not invertible on L2. However, if you add C naught into the problem, then you don't work with operator B alone. You work with an operator that looks like constant times identity plus operator B. And this operator, it's much nicer because this is in fact coercive and invertible on L2. So you can invert and then you're back into the usual framework of a parabolic equation. Okay, no issues. After this paper, there was a paper by Zenitsek in 84. He focused on the two-dimensional case, but his methods can be generalized to 3D. And he studies weak solutions, and he uses Roth's method. So what that means is that he uses discretizations in both space and time. And it's around 2000 that Showalter started looking at this problem. And what he did, basically, he developed the whole semigroup theory for implicit evolution equations of this type, where he discussed both weak and strong solutions and so on. Again, all this in the case of linear poroelasticity. Now, for nonlinear, Showalter had a paper a year later where he considered a nonlinear permeability, but it was a nonlinear function of the fluid pressure taken in such a way that you preserve a monotone structure of the problem. So you fall back into the semigroup theory that he had developed previously. And and this made sense for the applications in the geosciences that he was looking at. The first paper that considered a permeability nonlinear function depending on dilation was a paper by Cauchin and Meyer. But again, they only looked at the case of compressible constituents because, as I mentioned before, the problem becomes much nicer, and they simplified the boundary conditions, so just homogeneous Dirichlet boundary conditions. So what we did in our first paper in ARMA is we really built up on all this previous work, but we wanted to stay in the realistic scenario. So nonlinear coupling through permeability, which, it's a loss of monotonicity. We focused on incompressible constituents, and this destroys the parabolic nature of the equation because you lose the term that had P sub t in it. We had non-homogeneous mixed boundary conditions, which really means, if you work in elasticity, if we allow the two parts of the boundary, the Dirichlet and Neumann, to touch, you no longer obtain the maximal elliptic regularity for the solid displacement U. And we made a comparison between elasticity and viscoelasticity, right? This is what we wanted to look at as well. And I'm not going to go through any details, but just to point out that the first result in the paper really told us how different the solution is between those cases and how dependent it's on the data, right? So what turned out is that if you add viscoelasticity, everything is nice, right? You can have your data in L2. Of course, on the boundary, you need L2 in time H1 on the boundary, and you get solution in the finite energy. In fact, you get even better for the displacement. It's H1 in time. However, if there is no viscoelasticity, you're just pore elasticity, in order to get your finite energy solution, you actually need higher regularity in time for the sources F and G. So they need to be H1 in time to actually obtain solution. And I'm not going to go through details. The idea here is, of course, I just mentioned existence of weak solution. I said nothing about uniqueness because this is the nonlinear problem. And when we were thinking about this, we spent quite some time thinking about fixed point strategies, which is normal to think about when you have nonlinear problem, and we couldn't make it work. And I just want to point out what happens and how the two are very, very related. So, weak solutions are unique for constant permeability. There's no issue there. But the problem becomes non-trivial as soon as you move from constant permeability to even a function kxt. So even a function dependent on space and time. So there are uniqueness results in the papers I mentioned by Showalter, but with an additional hypothesis for the permeability. You need the time derivative of the permeability to be L1 in time, L infinity in space. Why is that? What the crux of the matter is the following, that there's no energy estimates for arbitrary weak solutions. You only have them for solutions that are constructed as limited approximations, okay? And the issue is why don't we have this is because we don't have the multipliers. So what happens, even if this is a quasi-static scenario, the desired multiplier in the first equation in order to cancel the coupling remains U sub t. In the second one, P. But U sub t does not have the necessary regularity to be used as a multiplier properly, right? So then, okay, so what do? You boost at the next level. Let's say I'm going to multiply the first one with U, and then the second one I have to multiply with the integral of P. And when you do that and you combine it with the second term in the second equation, that becomes an issue because in order to move forward, you need to be able to write it as a total time derivative of something. And because of that means you need assumption on K because that's part of the term. So you need to have an assumption on the time derivative of K. This was exactly the main impediment why we couldn't do a fixed point, because the fixed point will be constructed exactly through the permeability. So if I need to put an assumption on K, implicitly I have to put an assumption on my solution, which you cannot do. Okay? So that was the main issue there. We kept thinking about this, but I'm going to skip. We do have some results. We were able to, one way to approach it is, okay, you don't have uniqueness, but you can work maybe with fixed point strategies for correspondences instead, right, which are multi-value maps. We did that. Recently, we actually even were able to prove uniqueness of solution for the linearization system without further assumption on permeability. But these are done in more simplified scenarios where we had to simplify the boundary conditions. So we couldn't keep the full mixed boundary conditions from the application. But we do have some more recent results related to that. The other thing I want to mention here is that once we got, coming back to the application in the full general case, right? Once we had that result, a lot more questions came up, right? So what does it mean? So for example, if I only have L2 regularity for data, but it's only porous, no viscoelasticity, does it mean that the solution exists, but it's our approach that does not see it? Or does it really mean it's a blow up in the solution? And if it's a blow up, who blows up? Which energy? The energy of the elasticity or the energy of the fluid, right? So we did some numerical computations with respect to all sources, but I focus here just on the boundary one, on G, right? So just very easy, think about like taking a step source, right? So it's not continuous in time, right? So it's not H1 in time. So take a step source, 0, 1, 0. And what happens is you see two peaks that show up in the fluid energy exactly at the times of discontinuity in the source. Okay, and these two peaks increase as you let delta T go to 0. So lack of time regularity in the source G reflects into a lack of regularity in the fluid energy P. In comparison, if we add viscoelasticity in the systems, the peak diminish. There's no longer peaks, right? You can see it's like kind of smoothed out. So, of course, numerical computations are not a proof, right? But they do give you hints of what happened. So, okay, so then we said, can we actually prove this? And we could. If you go to one dimension, you can actually find explicitly the solution. You have like an undergraduate PDE course. You let them compute the solution. It's a series, right? You can show that the discharge velocity, in fact, blows up if you do not have sufficient smooth in time regularity for the stress, for the boundary data, and if you don't have any viscoelasticity in the system, okay? So really, this helped us come up with a hypothesis concerning the causes of damage in biological tissues, namely lack of structural viscoelasticity in combination with abrupt time variation in mechanical loading. So think of this as data, and for the eye, this boundary data would be exactly the intraocular pressure. Okay, so if you have sudden fluctuations in the intraocular pressure, and let's say you're in advanced age when the collagen in the tissue is no longer there, okay, this combination leads to a blow up in fluid velocity within the porous medium, which really means you have these capillaries. That means the blood will burst through the capillary, and that creates microstructural damage. And we were happy with this because it was supported by experimental and clinical evidences showing that loss of viscoelastic tissue property has been associated with various pathological conditions like glaucoma, which is what we were focusing on, but other diseases as well, like osteoporosis, renal disease, Alzheimer, and so on. Of course, once you see this, then the next goal is, okay, can we give some practical directions on how to control the biomechanical response of this tissue, right? So that's a different way to approach this. So you go into control and optimization, but that's not what I want to focus on today. We have some preliminary work on that, but I'll skip that. What I want to come back to, because this is what I told you in the beginning, is not just the local problem, right? We had focused on the local problem. I wouldn't say finished it, right? But we have some results on the local problem, and now we want to incorporate the global features, because this disease, clearly there are many factors involved in it, and there is some clinical evidence that the blood pressure of the person also influences what happens in the eye. So we wanted to account for the blood pressure, and this is what we do by basically modeling it with this lump hydraulic circuit, right? With this ODE, okay? Sorry, I skipped too fast, but these are the recent papers that we have related to this multiscale interface coupling. Two of them are based on numerics, and one of them is based on the theory. So let me just, 1 minute that I have, hopefully, just tell you what we've done for the theoretical part. And here I should mention that for the poroelasticity, I'm starting step 0. This is a linear system, okay? So permeability is a constant. Okay, so it's not nonlinear BO, so linear system for poroelasticity coupled with the ODE, but the ODE is nonlinear. Okay, and all the theory that we've done before for the BO system came in here, of course, because the way we approached this was by building a fixed point map. I think it's easier if I show you this slide to understand how we build the map. So basically, we start with the variable from the ODE. So I define a ball So I take a ball in L infinity of radius m. And first what I do is, remember, in the state variable, in the vector y for the ODE, the first component was little pi, which I told you was the most important one, right? So that's the one that comes into BO in the interface condition. So basically, given z, take the first component, that's little pi, and give it in this Robin type boundary condition for the BO, right? And this is which I called LBO, the map that solves the BO system, the poroelastic system, given little pi. Okay, once you solve BO, you have displacement and fluid pre, but then I know that through the interface conditions, I assume that capital P is the average of the BO pressure, so I take the average. Remember, through Poiseuille's law, I have this relation between capital Q and capital P, and that's what comes into the ODE, right? That's the connection with back to the ODE. So now, this is the new map. I solve the ODE once I give capital Q, right? Solve the ODE, and then I compose the two maps to give me my capital T map. And this is what I want to show, that T has a fixed point in the ball, okay? So this is a basic fixed point map. The hard part here is to show that there is a ball that stays invariant under the map, and this is where you can see that we weren't able to go all the way to capital T. So there exists a time, okay, T tilde we called it, but which is a little bit, it's less than capital T, on which this we were able to show invariance of this ball. The key here is basically all the we used all the estimates we had before on the poroelastic systems. Okay, based on the estimates, we were able to, and combining with the ODE estimates, of course, we were able to get this this bound on the ODE state. And the way to think here is, okay, the curve on the right-hand side is basically a monotonically increasing curve starting at y0, but y0 is strictly less than capital N. So if you think about the curve m squared times e to my exponential with a minus, right? The curve starts above. So one curve goes up, one down. So there must exist a time, right, up to which you stay below. That's the whole idea here. So there must exist this time up to which this part here stays below m squared e to minus, which then gives us that yt stays less than m. After that, the second part is easier. We can show that t is continuous and relatively compact, so it's compact, and then you apply basic Schauder's fixed point theorem and get that you have a fixed you have a fixed point, and then you get solution. Of course, what we're working on now is we don't want to have small. This is a local, small time, basically local existence, and now we're working to improve that to arbitrary capital T, of course. I'm probably out of time. What I wanted just to finish up, we also look at this problem. We did numerics on the problem, and we compared, I should say, functional iterations with an operator splitting method, because while the fixed point argument was successful for the well-Posner's theory, in fact, functional iterations, which are basically fixed point math, did not work well in the numerics. And the key thing here is that this problem really has the physical energy is dissipative, really. If you look at the whole energy of the system, okay, ignore sources. If you had zero sources, right, zero on the right-hand side, there are three dissipations coming into the system. One from the ODE, one from the fluid, but also one from the connection between the two. It gives a dissipated term, a strictly positive term on the left side. And in the numerics, once you discretize, the mismatch, you introduce a mismatch between the two when you separate the 3D and the 0D, and that mismatch leads to basically, like in the discretization, you lose the dissipation. You no longer get a strictly positive term. This only goes to zero if you have convergence of the algorithm. So that was the issue here. So numerical iterations did not work well. What did work well was the operator splitting method. Okay, but I have no time to go through the details, but just to point out, in this case, we were able to show that it's unconditionally stable with respect to the time step. And it's all based on the fact that it preserved the energy identity at the discrete level. And with that, I just want to get to the last slide to acknowledge all the people that have been involved in this, or my collaborators, in all these problems, and of course to acknowledge the support from NSF for many years. So thank you so much.
Okay, thank you. Let's right now open for questions or comments. Juan, the microphone is open for everybody or not? Yes, audio and video is open.
Can I start, Roberto?
Yes, of course, Eduardo. Go ahead.
Yeah, well, I don't know if it's has some biological meaning, Lorena, but replacing your lamp circuit by a one-dimensional PD, for instance, should be interesting.
Of course. Do you want to work together on that?
I open. I open.
No, I agree. Of course, there's many things to consider. Yes.
Okay, it will be nice. And well, another thing, well, because of your coupling, you know, you are working with the fluid without getting rid of the pressure, right? So, have you encountered in the literature some control results where the control acts on the pressure on the boundary, for instance? So controlling a fluid with from the pressure, from the boundary condition for the pressure.
So on the PDE system alone, we do have some results on optimal control related to that, and we were able to show that you can use all sorts. You can use interior sources, but also you can use boundary sources as control on the linear problem, on the linear poroelastic problem. But as you mentioned before, you were saying like you don't solve per pressure. So these problems are very different than the usual Stokes-Navier-Stokes, right? It's a different type of equation, and you don't have to, you know, get rid of the pressure in a sense, right?
Yeah, that's sure. That was, I was asking that. Thank you, Lorena, for a very nice talk.
Thank you.
Thank you, Eduardo. More questions or comments?
Please, good afternoon. I would like to make some question about.
Okay, Emma, can go ahead.
Okay, I would like to know about the results, the principal results about this work, and the numerical process for the solution.
I'm sorry, I did not hear the first question. The principal work, the first question, Roberto, did you hear?
No. Emma, can you repeat, please?
Yes, I would like to know about the practical results about this work, the practical, or the simulation in the clinical life, because I see the numerical result, but I would like to implication in clinical life.
Okay.
Yeah, so I should have said, and I went a little bit fast, but I can go back to the slide. Here we go, right here. So one of my collaborators is Dr. Alon Harris. He is the director of the Glaucoma Foundation and professor at Mount Sinai Medical School in New York. He's been working on glaucoma for decades, and they have lots of data from patients over decades, right? So and I'm not the person I'm not the expert on modeling, right? But one of my collaborators is, and they are the ones that started these models for parts of the eye many years ago, right? And I joined them, as I said, about 10 years ago to participate in this project more from the theoretical point of view and simulations point of view. But they do So they have enough data to validate their models. As I said, I'm focusing here, and especially in this talk, on small parts, but there's also a model for the retina. There's also a model for, there's many things that can be combined and looked at, right? And we are doing that, and we will continue to do that. So now, yes, your question is, well, how are they using? So they are using our work as an insight at this point, right? Of course, in a fantastic world, we would say, oh, let's build a digital twin for the eye, and maybe that is a goal. I don't know. We should dream big, right? Let's build a digital twin for the eye. But to do that, you need to model all these parts of the eye and put them together, right? And for a digital twin to properly work, you need constant measurements, right? So then I don't know how exactly that will be in these types of diseases, because these are diseases that develop over years, right? So these problems are the really complex one where you have multi-physics, multi-scale couplings, right? Digital twins work well in a surgery, let's say, when you have a patient in ICU. It's hooked up and they have continuous measurements, and they, that model, the virtual model, can gather data continuously and use it to control and tell you what to do. Here, I'm not sure exactly how this will work, but this is really if we can get close to whatever you want to understand by a digital twin of the eye, this is where we're going with this. Does that make sense?
Yes. About what you told me about the thermodynamic condition, because do you use thermodynamical condition in your problem?
I am not sure. I know what that means, thermodynamic. I don't know. If I care about temperature, is that what? I'm not
Yes.
sure I know.
Because I see some paper and use a thermodynamical condition about the deformation the problem. But well, my congratulations for your work. Thank you very much.
Thank you. Yeah, I'm sorry. I'm not aware of. No, we're not using a thermodynamical condition, and I'm sorry, I'm not aware of this literature. Sorry.
Okay, thank you. Thank you, Prof. Thank you, Dr. Lorena.
Thank you. Let's say thank you again for this beautiful talk of Lorena. Thank you, Lorena.
Thank you.
Hopefully see you again in July.
Oh, yes.